Hello, and welcome to another lecture in the course. So today we're going to look at homology versions of Cauchy. So really in some sense, the most general version of Cauchy that we're going to look at in this course. So, all right, let's start talking about homology. So this is a property of cycles, right, with respect to some domain, and there are cycles in this domain, right? Or actually, any open set doesn't have to be a domain, doesn't have to be connected. So if we have a cycle in an open set U such that the winding number of gamma of this cycle around every point in the complement of U is 0, then we say it's homologous to 0. Gamma is homologous to 0. Really, it just means in sort of more plain language, gamma is a cycle that does not wind around anything not in U. It doesn't wind around any point of the complement. All right. So now, one thing to keep in mind, homologous to 0 does not mean equivalent to 0. So it doesn't mean that integrals of continuous functions, see, it's going to be very different with holomorphic functions, but integrals of continuous functions doesn't necessarily have to be 0, right? These are not 0 or cycles equivalent to 0, right? These are just cycles that happen to not wind around anything around at the on the complement. So, for example, if U is all of the complex plane, then every cycle is homologous to 0. So it's definitely not equivalent to 0, right? There's lots of very interesting cycles in C, right? Now, the domain matters, of course, because we're talking about the complement of the domain. So the unit circle, let's say, going counterclockwise, that's homologous to 0 in C, but it's not homologous to 0 in C minus the origin. Right, because then it's going around 0, and 0 is not in the domain. So the domain matters. All right, so here is the version of Cauchy that we're interested in, that we're going to prove today. So suppose you have an open set and a holomorphic function on this open set, and you have a gamma that's homologous to 0 in U, right? So it's always with respect to this domain U, right? Then for every Z, it shouldn't be on gamma, because then it's not going to make sense. But every Z in U that's not on gamma, we have this formula that again, we have to put in the winding number, that just happens to be there. If we happen to wind around some point too many times, then we have to count it. But basically, the value of the function, right, taking into account how many times we wound around it, is equal to, well, precisely what we expect from Cauchy formula, right? So the integral around gamma of f over zeta minus z, right? So it looks precisely like the Cauchy formula for, let's say, the circle, right? But now it's for any gamma, as long as it's homologous to 0, and the one added complication is this, adding the number of times we wound around z, right? So you could, a lot of times when you're applying this, you actually have a gamma that only winds once around the points where you're interested in, right? So if you can pick the gamma, you don't have to. You can pick it so that it doesn't wind more than once around the points where you're interested in. So, for example, in the circle, right? In the old version, in the simple version that we did before, it was right. Everything inside the circle we wound around exactly once, right? So that winding number, this guy that's been in there, it was just one, right? All right, so let's prove this. And it's actually kind of a neat proof. Definitely not the original proof. So let's define a function g, and it's actually a function of two complex variables. It's going to be defined on the Cartesian product u cross u, and we're going to define it this way. We're going to give it when zeta, so it's going to be a function of zeta and z. When zeta is not equal to z, we're going to let it be the difference quotient of f. And when zeta is z, it's going to be the derivative of f. Now, leave it as an exercise to show that two things for this. First, that g is continuous, and it has to be continuous as a function of two variables, right? Not just continuous as a function of each variable separately. You have to show that it's actually continuous in both variables, and it makes sense, right? Because, you know, if you just intuitively, if you think about it, when zeta gets close to z, right, then the difference quotient should get close to the derivative, right? So, or more likely when z gets close to zeta, right? So, right. So that's one thing, that it's continuous. The other thing is that it's supposed to be holomorphic when you fix zeta and think of it as a function of z, that this is holomorphic, right? So fix zeta, and do this construction. Now, the only tricky bit here is when you're getting close to zeta, right? That's the only tricky part of this. But it's an exercise. It's not too bad. All right. So suppose that you've proved that, right? And it sort of makes sense that that's what would happen, right? I mean, this thing is, after all, this over here is clearly holomorphic when z is not zeta. So it's just at one point, right? And if you've proved things about derivatives in one variable, you might have noticed this sort of expression in there as well, right? So in undergraduate real analysis, you might have seen exactly this sort of expression. All right, so let's go on. So let's define a function h, and let's define it this way. And some of you may already notice that I'm cheating a little bit. So see if you can spot where I'm cheating before I say where I'm been cheating, or what's the problem with this definition. All right. So we define when z is in u, we define it to be the integral around gamma in terms of the zeta of g, right? So fixing z, right? Z is where I'm trying to evaluate this function. Now, if z is not in gamma and the gamma doesn't wind around z, so where the winding number is 0, then we're going to define it as this expression over here, which really is this part of the difference quotient without the f of z, right? Okay, and that's where the Cauchy formula will come in, right? That's the thing that you've seen in the Cauchy formula. All right. Now, h is defined for all z and c, right? I mean, when Z is not in U, then the winding number around Z is 0. However, and this is the thing that I was talking about, where we're cheating a bit. At some point, we have two definitions, right? I mean, there could be points in U that aren't in gamma and that we don't wind around. All right, so suppose that we're at those points. So we're in U, not in gamma. So we're in U minus gamma, and the winding number is 0. All right. So let's see if these definitions are different, right? So on one hand, we have this definition, right? This definition over here, and we're trying to show that it's going to be equal to this definition. All right. So we write down what that G is, right? Because Z is in U, right? And Z is not ever equal to zeta, because zeta is on gamma, right? And whereas Z is definitely not on gamma, we have this definition for G. All right. Now let's split it up. So as I said, it's this guy is actually this part of the difference quotient. So we'll split it up. We'll take this, and then we'll take minus the integral of this thing. Now, the integral of the second thing, right? If you look at it, right? Well, it's f of z times, right? Z is not being integrated. So we can pull f of z out of the integral of the second piece here, right? And then it's just the integral of 1 over zeta minus z d zeta, right? And that's, well, up to 2 pi I. That's the winding number of gamma around z, right? So, okay, we get, yeah, this looks very promising, right? We have both things that appear in the theorem. So good, but that's not what we're trying to prove. Right now, we're trying to prove that this guy is equal to this guy. Well, but here, the winding number around z, gamma, was 0, right? So this whole thing is 0. So that means that this guy is equal to this guy, and we're good. All right. So H is well defined. Now we want to show that H is actually holomorphic. Now, holomorphicity is a local property, so you only need to consider it in every neighborhood, right? So if you prove it in open sets that cover C, right? I mean, this is supposed to be an entire function, right? It's actually kind of weird because we're proving the Cauchy formula in an arbitrary domain, and we come up with an entire function, right? Anyway, so we just need to prove that H is holomorphic on any open set, as long as those open sets cover C, right? So we're going to do it on 2 open sets. So first, if we look at the set of Z, which are not in gamma, and where the winding number is 0, so this is some union of components of C minus gamma, right? And those are open. So that's an open set. And clearly, H, which is this function over here, that's holomorphic there, right? On those guys, that's the definition. right? Because, well, I mean, it's a function of z, and so we have this lemma, right? That we could, if we had an integral of something, that had an extra variable in there over some cycle or chain, doesn't really matter, and that inside was holomorphic in that extra variable, then the whole thing was holomorphic, right? As a function of that variable. So we have that z here, we have that z here. So inside is clearly holomorphic, right? Okay, so we're applying that. So this guy is holomorphic. Now, the other open set that we're looking at is U. And so U is open. And by the way, U together with the set where the complement of gamma where, or the union of the components of the complement of gamma where the winding number is 0, those two open sets cover C, right? So it's enough to consider those two, right? So if we take Z in U, right, then over there we have this is the definition, right? It's just integral of G, right? And well, you've proved that that G is holomorphic as a function of Z, so therefore this is holomorphic. All right. So H is holomorphic. It's an entire function. All right, so let's consider Z on the unbounded component of the complement of gamma. Right, so maybe very far away from the origin. Right, actually, we're going to want it to be very far away from the origin. Now, on the unbounded component, we have that the winding number is 0. So there we have this definition for H, right? It's just basically looks like the Cauchy formula. All right. Now, on gamma, we can bound what F is. I mean, gamma is a compact set. So, and F is holomorphic, so it's continuous, right? So, yeah, it has some bound, right? So we're gonna call M the bound, and we're gonna call L the length of gamma, right? There's some finite length, right? And let's consider H of Z. I'll write down what the definition is, and now we push the absolute values inside. Again, that you have to push them on the d zeta as well, right? So we're getting less than or equal to. We're bounding this from above, and well, the top is bounded by M, and the bottom, right? We can bound this. Well, we bound the gamma by L, the size of the length of the gamma, right? So we get rid of the integral, and we bound over here the bottom, right? Is bounded by this is zeta minus z is bounded from below by the distance of z to gamma, right? So 1 over zeta minus z is bounded from above by 1 over the distance from z to gamma, right? So we get this estimate for H. Now, if we take z going to infinity, then the distance from z to gamma, of course, goes to infinity. Because gamma is just some compact set. Therefore, H goes to 0. Well, that means that H is bounded. If H is bounded, Liouville says that it's constant, and the constant has to be 0 because it goes to 0, right? The only constant that goes to 0 at infinity is 0. So what do we have? If we look at any z in u minus gamma, then we have that h is 0, right? We proved it's 0 everywhere. So in particular, in u minus gamma. Well, what is h on this set? Well, on this set, it's always given by this thing, right? Because it's g, but on when z is not on gamma, right? Then zeta is never z, right? In this in this thing, so that's how we define g on that set, right? So it's this guy, and we do exactly the same thing as before, right? We split up this this difference quotient, right? And in the second integral, we pull out the f of z, right? And we just get the, well, up to the 2 pi I, we get the winding number of gamma around z. And now we know that that's actually 0. So yeah, that's precisely, this being 0 is precisely the Cauchy integral formula. So we're done. Right? It's kind of a slick proof. All right. So let's use. So we're actually going in reverse now. Let's prove the Cauchy theorem in terms of the Cauchy formula. Before we did the opposite, right? So let's prove the homology version of Cauchy's theorem. Right? If I have a holomorphic function on U and gamma is a cycle homologous to 0 in U, then the integral of f around gamma is 0. And the proof is almost trivial with the Cauchy formula, right? So fix z in u minus gamma. Right? Now apply the Cauchy formula to this function over here. Right? I mean that's a perfectly good holomorphic function now of zeta. Right? I mean I'm just multiplying by zeta minus z, right? Z is a constant. We're fixing z. Right? And we're gonna apply the integral formula. We're going to apply it exactly at the point where zeta is z. All right. So what does that mean? Well, if I plug in zeta equals to z into this thing, I just get 0. Right? So 0 is the winding number around of gamma around z, whatever it is, times 0 times, well, whatever f is at z, right? But now this guy over here, I can write using the Cauchy integral formula. That should always be equal to this thing, right? I have the function up here, z is fixed, right? I have the function up here, right? And divided by zeta minus z, and I integrate around gamma. That's supposed to be 0. But now the zeta minus z cancels, and so we have precisely what we want to be 0, right? It looks maybe, a little bit like cheating, right? It's, but yeah, sure, right? Basically, we've made the function 0 at this point z, and then we evaluated that function there using the Cauchy integral formula, right? And we get precisely the thing that we want. All right. Now, the Cauchy integral formula and Cauchy theorem, whatever versions you're working with, they're always logically equivalent. You can prove one from the other. So, you don't have to always go in this or that order. You can prove one if you have one, you can prove the other, and vice versa. So just sometimes, one of these proofs is easier or easier to follow, right? So that's why we were doing. So we did sort of both, both approaches, right? All right. So they're kind of the same theorem, right? All right. Now we had homologous to 0. So what about homologous to something else, right? Well, we really have we can really define this equivalence class of cycles. So if we have two cycles, gamma 0 and gamma 1 in U, then we'll say that they're homologous if their winding number around points in the complement are the same, right? So gamma is homologous to 0. Well, that was basically just saying that it is homologous to the 0 cycle, right? To the cycle that doesn't do anything, right? It always returns 0 when you integrate anything over it, right? So we just define this more generally. It just gives you an equivalence relation on the cycles in U. And so another way of stating it is that gamma naught and gamma 1 are homologous if you subtract them, then you get something homologous to 0. Now, how do we how does this fit in, let's say, to the Cauchy formula, right? So it's the corollary of the Cauchy theorem, sorry. So if we have two cycles that are homologous, then if we take a holomorphic function f and we integrate against those cycles, the integrals are equal, right? So where is this useful? So it's useful if you're computing an integral over some complicated cycle. Well, you can make a simpler cycle that is homologous, right? You just have to figure out that it is homologous, right? And then you can compute your integral against this simpler cycle, right? Where you might actually be able to compute it explicitly, let's say, right? Or you might be able to do something. So that would be sort of the application of this. But it has for example, forgot I was going to give an example. So for example, if we have any cycle in C minus 0, it's always homologous to some multiple of the unit circle, right? So unit circle going around counterclockwise, and some multiple of it, possibly negative multiple, right? But some multiple of the unit circle, right? So if you know how to compute integrals around the unit circle of any function holomorphic in C minus 0, you know how to compute integrals around any cycle of functions holomorphic in C minus 0. All right, you just have to figure out what cycle what n your cycle gives, right? All right. Now this actually leads into topology and homology groups. So this equivalence relation gives equivalence classes, and these equivalence classes, well, you get an abelian group, the homology group of U, right? Of any particular open set, and that really studies how many holes does U have. But it's more complicated than that. But for open sets in C, it really is just that. So it's it sort of studies the topology, how complicated the topology is of U. So we're actually going to look more at that next time. We're going to look at actually domains without any holes, the simply connected domains. So ones where, well, every cycle is going to be homologous to zero, where the homology group is going to be trivial, right? We're not really going to worry about the homology group or trying to compute these things, but that's where it ties in. It really has to do with the topology. All right, so see you next time.